Hello everyone and welcome back to a brand new episode of the Funtastic Academy. In this episode, we'll be wrapping up our three-part series about the floating point standard. This time, we'll cover some of the more detailed minutiae of the floating point standard. Stuff like infinities, NANs, subnormal numbers, and even negative zero, which is somehow different from positive zero. Trust me, it gets complicated. But don't worry, because in this episode, everything will be explained in a simple way. Now, of course, before we can pass the mic to Computer Ayush on his spreadsheet, we need to cover last episode's quiz question. Now, the question from last episode was, in the IEEE 754 single position floating standard, what is the bias that's added to the exponent? The answer is, drumroll please, 127. To represent negative exponents as a positive bias binary number, 127 is added to the exponent's value. The general formula for this, if you have e bits in the exponent, where e is 8 in our scenario, is 2 to the power e minus 1 minus 1. So, without a delay, let's pass the mic to Computer Ayush and dive in. For that, Cam Ayush. Now, over to me, Computer Ayush, with everyone's favorite trusty floating point spreadsheet. Now, as I mentioned in the intro, we are going to be discussing the more interesting types of floating point numbers. Quite conveniently, I have a column here labeled type that shows the type of number that we are storing. Now, if we click on this type column and see the formula, because remember, all of this is made with standard macOS numbers formulas, we can see that I have written down 5 specific types of numbers that this system can represent. First, there's the normal number. This is just the standard type of number that we've learned how to represent so far. You have a sign bit, you raise 2 to the power of the exponent, and you multiply that by the mantissa plus this invisible magic 1 that we always put there to save space. But we also have these 4 other types of numbers: 0, subnormal numbers, infinites, and not a number. Let's go to all 4 of these types of numbers in order and explain how they work, how they're different, and what they're used for. So starting with 0. 0 might initially seem obvious to represent. You just represent it at all zeros and use the same technique we talked about earlier. Where's the issue in that? Well, the issue is this invisible magic 1 we had over here. Now, I mentioned last episode that the reason that we can put this magic 1 is essentially because every number in binary starts with 1. And that's true for every number except 0. 0 obviously only has zeros. We can't insert this magic 1 here to save an extra bit. We really have to set our mantissa to all zeros. So we need a special entire case for the number 0. Now, you could do something like just reserving the entire 0 exponent, actually minus 127 because of the bias. You could just reserve all of this for the number 0. But the issue with that is that now we can put anything in this mantissa and will basically be ignored because this entire exponent is being reserved. So this sign bit plus these 23 mantissa bits, 75% of the number is just being wasted. So instead, the designers of the floating point format came up with a much more clever strategy. If the mantissa is all zeros, reserve that for the number 0. But if you add something else into the mantissa, then it's a subnormal number. The concept of a subnormal number is treat this exponent we have here not as minus 127, but as a minus 126, like the next highest exponent. But ignore this magic 1 that we insert here. So this number would be represented as 1 times 2 to the power of negative 126. Well, not actually 1. We would insert a 1 over here. Since we have 23 digits here, we have to bias by that amount to the exponent. But this is a much, much smaller number than we could have represented before. If we set the exponent to 1, you can see that with a classic normal number, this magical 1 comes all the way into our mantissa. But by representing a subnormal number, you can suddenly represent much, much smaller values, around 10 to the power negative 45. So, a 0 is when all of the exponent and the mantissa is 0, whereas a subnormal number is when you have all zeros in the exponent, but you have something in your mantissa. In this case, you treat the exponent as a 126 instead of 127, but you ignore the magic 1. Now there's one more extra point I'd like to bring up here. Negative 0. If we change the sign bit here from 0 to 1, you can see our sign is now minus, and we have result negative 0, different from 0. I actually had to write a whole entire special case in the spreadsheet in order to get negative 0 to work. And you might think, what's the point of negative 0? Isn't that just the same as positive 0? Well, no. See, in floating point numbers, there'll always be some degree of imprecision. And that's why we don't really consider these to represent an exact value. Rather, we treat them as a range of values. So for example, if I just have the positive 0 from earlier, that isn't just 0. It's any number that's closer to 0 than any other floating point number. Any number that's closer to 0 than to whatever this number is. So positive 0 just represents a really, really small positive number. And you can see how negative 0 would be useful now. It represents an infinitesimally small negative number, which is a different concept from the positive 0 that we had. So, now that we're up to speed on subnormals and zeros, let's talk about NANs and infinities. Well, just like how a completely zeroed out exponent can represent the smallest possible number, a completely filled out exponent of only ones represents the largest possible number, infinity. You can see here that we have an infinite type number. Result, infinity sign. Now, I can simply adjust the sign bit to get a value of negative infinity. Neat. But what about this rest of the mantissa? Like I said earlier, this is almost 75% of the number going completely wasted. Well, the designers of the floating point standard decided to take a similar approach of what they do 0, but this time using to represent errors. So if this mantissa section is fully grayed out in zeros, then I have either infinity or negative infinity. But if I put any value into this mantissa, then we get NaN, or not a number. Now, NaN is a really special case. It's one of the only things in the floating point standard or most programming languages which isn't equal to itself. If you ask a language like JavaScript, NaN equals to NaN, you'll get false. But NaN can be used to represent a huge variety of errors. We actually have 23 bits here to represent anything you want. So 2 to the power of 23 possible error codes, plus the sign if you want to repurpose that as well. So, NANs are used to represent computations that can't really be calculated as a result. You might think that this would cover things like 1 divided by 0, but it actually doesn't. See, 1 divided by 0, as we mentioned, means just 1 divided by some really small positive number. And that, we know that it's a really big positive number, also known as infinity. So 1 divided by 0 isn't undefined or NaN, it's simply infinite. But if you try to execute something like 0 times infinity, well, that's NaN. There's no way to really answer the question really small number times really big number. So we just get not a number, undefined, NaN. So that's it. We've covered the 4 extra types of floating point numbers: zeros, infinites, subnormals, and NANs. Now, back to camera Ayush for a recap. Thanks for that, Computer Ayush. Let's do a recap of everything that we learned today. We first learned about how zeros are represented in floating point. We learned how the negative 127 exponent can be repurposed for subnormal numbers and how negative 0 can be used in a reasonable way. We then learned about how the 138 exponent is reserved for infinities and NANs, and how NANs can arise from some unexpected floating point computations. So, to finish off this episode, I leave you with a simple quiz question. In mathematical notation, what is the exact value of the smallest possible positive subnormal number in the single position format? Tell me the answer, and I'll see you next time on the next episode of the Funtastic Academy. Bye!